Straight here again. Today we have notes for section 1.3 measurement. How old are you? How tall are you? Answers to these questions are measurements. Measurements are very important in both science and everyday life. Hard to do any science or hard to have anything in everyday life without measurements. In using measurements, we often use scientific notation. One of our key questions, why is scientific notation useful? Scientists often work with very large, very small numbers. Such as astronomers estimate there are 200,000 million stars in our galaxy. Really big number. Scientific notation, definition, way of expressing a value as the product of a number between 1 and 10 and a power of 10. So speed of light, about 300 million meters per second. Scientific notation, we write that as 3.0 times 10 to the 8th meter per second. Here, a really big number, we get positive exponents, decimal point to the right. Numbers less than 1, written in scientific notation, we get an exponent that's negative. So really small numbers and negative exponents. Here's a really small number. Snail's pace. 0.00086 meters per second. Scientific notation, 8.6 times 10 negative 4th meters per second. Negative exponent, how many decimal places there are to the left of the 8.6. You can use scientific notation in calculations. Here we're going to figure out how to calculate the distance light travels in about 500 seconds. So we express the speed of light, 3.0 times 10 to the 8th meters per second. Multiply that by 500 seconds, expressed in scientific notation, 5.0 times 10 to the second. Here we take the 3 and the 5 and multiply and get 15. Take exponents and add them and get 10. And we just have to do a little adjusting. We don't want 15, but we want 1.5, so we move the decimal back to the left. Made this number smaller. Moved it one spot, so we make the exponent 1 bigger. And it's 1.5 times 10 to the 11th meters. The approximate distance between the sun and the earth. When we divide, we're going to divide and subtract the exponents. So here we're going to figure out how long it takes light to get from the sun to the earth. Here we take the distance, 1.5 times 10 to the 11th meters, divide it by the speed of light, 3.0 times 10 to the 8th meters per second. We divide the numbers, divide the 1.5 by 3.0 and get 0.5. We subtract the exponents, illustrated there, get a 10 to the 3rd, again a little adjustment. We don't want 0.50, we want 5.0, so we move our decimal one spot, making this number bigger. We've got to make the exponent one smaller. So 5 times 10 to the second seconds, or 500 seconds. Another example, rectangle parking lot has a length of 1.1 times 10 to the 3rd meters and a width of 2.4 times 10 to the 3rd meters. What's the area? As we go through problems, and we'll be using this procedure frequently throughout the year, we look at What information are we given? Here we're given the length and the width. We always try to figure out what we're trying to find. In this case, we're trying to find the area. We need a formula, and we substitute into the formula. Now when I write these out, and as we do them during the course of the year, I'll be writing them out using a little calculation box like this. So we do 1.1 times 10 to the third meters, put 2.4 times 10 to the third meters. Just a nice way to keep track of our information. We go ahead and we multiply the numbers, so 2.4 times the 1.1, and we get 2.6. We add the exponents, the third and the third gives us 10 to the 6, and then meters times meters is meters squared. So altogether we get that 2.6 times 10 to the 6 meters squared. As in class, we will be doing a number more problems like this, and I'll explain much more about it. Anyway, I think, does the answer make sense? If the units are right, very likely your work's going to be okay. So what units, another key question, do scientists use for their measurements? And we got SI units of measurement. So, and that's the International System of Units, or SI, abbreviation for Système International des Unités, developed in France in 1791. That's why it's a little foreign language sounding. It was French. Very similar to the metric system. Scientists around the world use this system of measurement, so it's very easy to interpret each other's measurements. If we use different measuring systems, it would be harder. It'd always be having to convert, so it'd be harder to deal with these things. So scientists throughout the world use the SI. In science courses, we will always use SI units. And we must have units. It's a great little example. If somebody said they finished an assignment in 5 what? Could be 5 minutes, 5 hours, 5 seconds, 5 days. Could be a lot of different things. If I was going to have you mow my yard, and I said I was going to pay you 5, that could be 5 cents, $5, $500. Could be all kinds of different things. Could be 5 pieces of candy. Could be 5 anything. So we need units. Here as these students are using a thermometer, measuring temperature, we're going to use degrees Celsius. SI, built upon 7 metric units we call base units. SI base unit for length, straight line distance between 2 points, is the meter. Base unit mass, quantity of matter in a sample or in an object, is the kilogram. Here's all of the base units. We've defined length, we've defined mass. As we go through the course of the year, we'll do quite a bit with temperature. Here our unit is the Kelvin, capital K, and we use it a lot with time. And our unit's the second. Briefly in this course, we'll talk about the mole, unit for the amount of substance. Many of you will take chemistry later. We work a lot with the mole in chemistry. Electric unit, we briefly touch on it. The amp and luminous intensity, candela, and this will, other than at this point, we probably won't do anything with the candela in this course. Then we have a lot of other units we call derived units. They're made up from combination of base units. Volume is a derived unit. the amount of space taken up by an object. Density is a derived unit. The ratio of an object's mass to its volume. Time with derived units, you end up having formulas that relate to them, such as density equals mass divided by volume, our formula for density. Here's a list of some very common derived units. Area are units, one of our units we use, square meter, volume, cubic meter, density, kilograms per cubic meter, pressure, Pascal, energy, joule, frequency, the hertz, electric charge, the coulomb, and then this little areas that show what these units are, made up from the base units. Most of these units during the course of this year we will be working with. So to derive the SI unit for density, you divide base unit for mass by the unit for volume, and we get kilograms per cubic meter. Many other units for density we actually either use too. Grams per cubic centimeter are a very common unit for density. Gold has greater density than feathers. At other times when we think something is heavier, like we'd say gold is heavier than feathers, and then gold's more dense than feathers is what we really mean. Very key thing we use in science is metric prefixes. Here's a nice list of metric prefixes, some of which you've heard of and worked with before, like kilo means 1,000, like a kilometer is 1,000 meters. You should have heard of centa, like a centimeter. There's a centimeter is 100th of a meter, or there's 100 centimeters in a meter. Milli is another very common one. In computer technology, you may have heard of mega and giga. There's other ones that are bigger than this, like tera. And got some other real small ones, micro and nano, and then there's even smaller ones than that. This chart, all right, go on. This chart, make sure you have this in your notes, in a very useful place to use it. So if you have 9 ms, standing for milliseconds, that means there is 0.009 seconds. We divide it by 1,000 to get to the seconds. Or you get 12 kilometers is the same as 12,000 meters, because each kilometer is 1,000 meters. So kilo means 1,000 meters. 12 times 1,000, 12,000 meters. Gigabyte, I mentioned earlier, computer technology, means we got a billion bytes. A megapixel is 1,000,000 pixels. Conversion factors we use to do some changing. Conversion factors is these equal units, like a kilometer is 1,000 meters. A meter is 1,000. 1,000 meters is a kilometer. Two equivalent conversion factors. And we can use these to change. We take 8,848 meters times 1 kilometer over 1,000 meters, a conversion factor. The meters divide out. We're left to kilometers. We do a little division, we get 8.848 kilometers. Or in the other direction, we flip the unit over, kilometers cancel, and multiply 8,848 meters. So, in science we do number conversions. We use conversion factors for a lot of different things. And we get some things to limit how we report things, limits of measurements, and how does the precision of measurements affect the scientific calculations. Precision is a gauge of how exact a measurement is. We talk precision, we deal with significant figures, and there are all the digits that are known plus one estimated digit. And as we do calculations through the course of the year, I'll be talking a lot about significant figures and precision and how we report answers. Our key here, the precision of a calculated answer, is limited by the least precise measurement used in the calculation. So, here's a couple different clocks. A digital clock is precise to the nearest second, so we know this is precise to the nearest second. While the analog clock is precise to the nearest minute. So the digital clock is a more precise measuring instrument. So when we do calculations like calculating density here, mass divided by the volume, 34.73 grams divided by 4.42 cubic centimeters, the calculator is going to give you a whole bunch of digits. But we don't want to report all those digits. We can only report the smallest number, the least precise number. So here we had 4 sig figs. Bottom part had 3 sig figs, so we get to keep 3 in our answer. So we round this to 3 digits, and we get 7.86 grams per cubic centimeter. As we continue on, we will be doing a lot of work with this thing through the course of the year, especially as we move into the second semester when we cover physics. Accuracy, another related thing. Accuracy is the closeness of a measurement to the actual value. So is it actually the right answer? So the right number. Precision is basically how many decimal places we can report. Accuracy, is it really the right thing? If a digital clock was running 15 minutes slow, we could use that clock. It's always going to be wrong. It's always going to be off. It's not going to be accurate. Measuring temperature. So I got a thermometer. Temperature measures temperature, or how cold a substance is. Not a great definition for temperature. So when we cover a unit on heat, we'll give you a little better definition for temperature. So, temperature thermometer, have a Calipari tube, just a real narrow tube. We fill that with a colored liquid. Used to be mercury, now it's usually alcohol with food coloring in it. Got a bulb down at the bottom of the tube to contain a supply of liquid, and then you scale it up the sides. As this thing heats up, the liquid expands, it's going to come up the tube. As it cools down, the liquid contracts, and it's going to fall down the tube. And the scale is set up so that we have temperatures. If we had a big tube, we wouldn't see much of a rise in the liquid, so it wouldn't be very easy to tell the temperature. But with a narrow tube, a little change in temperature causes the liquid to shoot up, or when it cools down, to come down the tube. Great distances. Here again, these little tiny distances. So the markings would be really close together, really hard to read. Couple of very important formulas you should have seen before is how to convert from degrees Celsius and degrees Fahrenheit. Couple key little things to remember. A degree Celsius is about twice as big as a degree Fahrenheit, actually 1.8. And then remember the formulas. So those couple temperature scales you've heard of before. The actual the SI unit for temperature is the Kelvin. Not degrees Kelvin, just Kelvin. Temperature 0K or 0 Kelvin refers to the lowest temperature possible that can be reached. We call that absolute zero. This corresponds to about negative 273.15 degrees Celsius. And that what we use to convert between Celsius and Kelvin. Get this K equals degrees Celsius plus 273, or degrees Celsius equals K minus 273. Here's some nice little chart you want to make sure you have in your notes. This gives some very key temperatures and things you're going to remember, like water boils, water freezes, average room temperature, human body temperature. And then we have a few quick review questions. Shopping mall has a length of 200 meters and a width of 75 meters. What's the area of the mall? So here we just want to do 200 meters times 75 meters. So I was doing this problem, I just go ahead and do it in standard notation, and we'll change it back to scientific. So 200 times 75, 2 times 75 is 150, and we'll just add those two zeros back on. So it's 15,000 meters squared. Scientific notation is going to be 1.5 times 10 to the 1, 2, 3, 4. Big number, positive 4 meters squared. So that appears that we have an answer of, C. C. Here we get a volume of 50 milliliters. We got a mass of 78.43. We divide those, 78.43 grams divided by 50.0 milliliters. I already told us we get that on our calculator. Grams per milliliter. A milliliter does happen to be the same thing as a cubic centimeter. So grams per cubic centimeter, another way we could express it, as they have here. We just have to round it to the correct place. And 78.43, 4 sig figs. 50.0 has 3 sig figs, meaning we only get to keep 3 in our answer. And there's where we rounded it to 3. So our answer is B. And how can you convert a temperature expressed in Kelvin to degrees Celsius? It's always going to be the 273, so definitely not those two. Now, you just have to remember whether add or subtract. And with degrees Celsius, we can get very small numbers. Kelvins ends up being a little bigger number, so if we're going from Kelvin to degrees Celsius, the Kelvin's always going to be bigger than the degrees Celsius, so we need to add the 273. SI base unit for length is the mile. Definitely false. Miles an English unit, or SI unit for length is the meter. And that's it for section 1.3 notes, and we can always add things from your textbook also. Put anything you want to in your notes. Example problems here it did in could end up being a quiz question. But always take as good a notes as you need to succeed on our quizzes and tests. So that's all for now. Till next time, it's a stripe.